Good evening, everyone. So we'll start a new topic today, which is about the chemical energetics, energy from the chemicals. In this chapter, we'll discuss about the energy changes during a chemical reaction, how we can calculate the energy change for different types of reactions. Basically, how we define the enthalpy change. Enthalpy change is the energy change which occur during a chemical reaction. We call that as enthalpy change. For example, if energy of the reactant, we call that as H1, and energy of the product, we call that as H2. So the enthalpy change the difference in energy of the product and the reactant molecule, that is denoted by delta H, which is equals to H2 minus H1. So when we carry out a difference in energy between the reactant and the product, we call that as enthalpy change. So in terms of chemical energetics, the reaction can be a reaction in terms of chemical energetics. It can be an endothermic reaction. The term endo means in, so reaction in which energy is taken in, we call endothermic. Or in terms of enthalpy change, the reaction can be exothermic. The term exo means out. So if a chemical reaction occur and it release energy, we call that as exothermic reactions. So what will be the enthalpy change when a reaction, if a chemical reaction is exothermic or endothermic? So how we can work out this? Example, we have the reactant, because always in the beginning what we will have the reactant, and reactant will form a product. So if you want to draw energy profile diagram for this, so this one is representing the energy of the reactant. Now what happened? Example, the reactants are absorbing energy. When the reactants absorb energy, the energy of the reactant will increase, and they will reach a certain energy where they start to react. In the beginning, they're absorbing energy, they're colliding with each other, but they're not forming any new substance, so the product is not formed. The moment when they start to form the product, the moment they start the reaction, the minimum possible energy for which the reaction start, that is called activation energy. So from reactant to the point where the reaction start, we call that as activation energy. And once the product is formed, like as the reactants are forming a product, bond forming is exothermic, so they will release some energy. So during a chemical reaction, when there is a chemical reaction, some of the energy, like there is always energy absorbed, energy is taken in to reach the activation energy, and energy is given out. But you can compare the two things here. The energy taken in is more than the energy which is given out. So in terms of chemical energetics, this reaction, most of the energy it absorbs and very small amount is released. That is why this reaction is known as endothermic reaction. So in endothermic reaction, the energy, more or greater amount of energy is taken in, and small amount of energy is released, but in comparison it is smaller. And what is the term enthalpy change? The term enthalpy change means the difference in energy of the reactant and product. When we take out this difference of the energy between the reactant and product, what we call that as Enthalpy change, if energy of the reactant is denoted by H1 and energy of a product is H2, so it will be H2 minus H1. And as you can see, the enthalpy, the energy of a product is higher than energy of the reactant. So when we take out the energy difference for endothermic reactions, what we will get? We will get a positive answer. So this is energy diagram, enthalpy diagram for endothermic reactions. Same thing will happen if you have an exothermic reaction. So as you can see, this is for endothermic reaction. Sorry, this is for exothermic. The opposite, the one which I already explained, the endo I explained to you. Now what happened in exothermic reactions? So we have both reactant and product. Like in the beginning we have reactant. So first what happened, the reactant, because reactants are not having energy to instantly react with each other, they need a certain amount of energy to start up a reaction. So energy which they need to start up the reaction, minimum possible energy at which the reaction start, that minimum possible energy is called activation energy. Once they reach the activation energy, they will form a product. When they are forming a product, bond forming is exothermic, so it will release energy. But in this example, you can see the energy which is absorbed or taken in is small, but as a result, greater amount of energy is released or given out. So in terms of chemical energetics, a small amount of energy is absorbed and greater amount of energy is being released. So this reaction is known as exothermic reaction. And if we say energy of the reactant is H1, energy of the product particle H2, so when we calculate the enthalpy change, energy difference, so it will be H2 minus H1, and H2 is smaller, so the difference will be negative. So for exothermic reaction, enthalpy change is always negative, and for endothermic, enthalpy change is positive. And the difference in the energy between the reactant and the product, that is known as enthalpy change, denoted by delta H. Now what happened during a chemical reaction, endothermic and exothermic, as you can see, this is the part energy which is absorbed, a small amount of energy is absorbed, but as a result greater amount of energy is released. The overall reaction is exothermic, and what happened to the energy released? That energy is transferred to the surrounding. So when the energy is transferred to the surrounding, the product will have low energy and the surrounding temperature will increase. Some common exothermic reactions are there, such as combustion of the fuel or oxidation of carbohydrates such as glucose in respiration. Both produce heat energy. For endothermic reactions, what happens? The reactants have low energy, where the product will have high energy, or energy which is taken in to reach the activation energy is higher as compared to energy released when the product is formed. So overall reaction will be endothermic, and energy taken in is higher than energy released. So in endothermic changes or endothermic reactions, heat energy is absorbed, greater amount of energy is absorbed from the surrounding. That's why the surrounding temperature will decrease. And the examples of endothermic reactions like thermal decomposition, dissolving, these are some examples of endothermic reactions. Is it clear to everyone? The two types of reaction, endo and exo. This is what you took in O levels as well. Like there was a chapter in which chemical energetics or bond energies. Any doubt till now? Now, there are certain reactions, we categorize them in terms how they occur. Example, like when you're burning something, you call that as enthalpy change of combustion. When elements form a compound, we call that as enthalpy change of formation. Like example, magnesium is element, chlorine is also an element. So when elements react and they form the compound, what we call that as enthalpy change of formation. Iron is there, reacted with oxygen, form iron 3 oxide. So what we also call that enthalpy change of formation. Why formation? Because the element on the reactant side, you have element and the product is a compound. So when elements in their standard state forming a compound, we call enthalpy change of formation. But the term standard enthalpy change. So what is the meaning of standard? So in standard enthalpy change, we keep or make certain standards, what like certain things fixed. So what is the standard term? What is the meaning of this standard condition? It means that the pressure is 1 atm or 100,000 pascal. The temperature, is 298 Kelvin, which is about 25 degrees centigrade. And the concentration of the solution, it should be 1 mole, and all the substances have their normal state. Like example, what is the state at 25? That state you will use. So example, magnesium, which is solid at 25, and chlorine, which is 25 here refers to the room temperature. So chlorine, which is a gas at room temperature, when they react and form a compound, when element form a compound, what we call that as enthalpy change of formation. If conditions are not standard, like example, maybe the reaction occur at 30 degrees, 35 degrees. So what how will denote? We'll say standard enthalpy change of form. We'll say only enthalpy change of formation. But if we carry out a reaction at a standard conditions, so if we carry out the reaction at standard condition like enthalpy, so we will write this symbol that shows that this is done at standard condition. Then what is the meaning of standard enthalpy change of? What is the meaning of standard enthalpy change of combustion? So when we burn a 1 mole of a substance at standard condition, like example, we are using methane as a fuel. So when we use methane as a fuel, we burn methane, it gives carbon dioxide and water. So under standard condition, when we burn 1 mole of a methane, it releases energy, and that energy which is released, we call that as standard enthalpy change of combustion of methane. So standard enthalpy change of a substance is defined as enthalpy change that occur when 1 mole of a substance is burned completely in oxygen under standard condition. So example, we burn methane, it react with oxygen, give carbon dioxide and water, and the reaction is exothermic, so the enthalpy change will be negative. But if it is a combustion, so that delta H is representing So C, because it's a combustion, so we'll write subscript C, and if it is done at standard condition, we'll write the symbol for. So definition of enthalpy change of a reaction: enthalpy change of a reaction when number of moles of reactant are specified in balance equation react together. So how we can calculate these enthalpy changes, and what is the meaning of standard enthalpy change of neutralization? So standard condition, the standard enthalpy change of neutralization means when a solution of acid react with an alkali under standard condition to produce 1 mole of water. Like example, you have say HCl, and this HCl is reacting with NaOH. So when they react with each other, this will result in a formation of salt such as sodium chloride, and it will produce water. So energy change which occur, what we call that energy change? We call that energy change if it is done at standard condition. So we'll call that as neutralization. And as you can see, 1 mole of a water is formed. So when we form 1 mole of a water by reaction of acid with alkali, we call that as standard enthalpy change of neutralization. And what is the meaning of standard enthalpy change of atomization? The term atomization means when we form 1 mole of an atom in a gaseous state. We call that as standard enthalpy, if that is refers to atomization of element. Like example, sodium is solid at room temperature. So at room temperature, sodium is solid. We supply energy so that we have a sodium vapors, like sodium atom in a gaseous state. So what we call this energy change, we call standard enthalpy change of atomization of sodium. So when 1 mole of a gaseous atom form from its element, we call that as standard enthalpy change of atomization. If there were 2 moles, then it will be twice. Like example, if you have oxygen, oxygen is O2, oxygen is gas. When you form 2 moles of oxygen atom, then what we call that as atomization, but that is not for 1 mole, that is for 2 moles, because you are producing 2 moles of oxygen. So to get the 1 mole, when we write a balance equation like oxygen is O2, so if you have a half oxygen, according to theory, if you have half oxygen, it will produce 1 oxygen atom in a gaseous state. If you have half oxygen molecule, it will produce 1 oxygen atom in a gaseous state. And what we call this, we call that as standard enthalpy change of atomization. So basically, how much energy is needed to produce 1 mole of a gaseous atom from its element, we call that as standard enthalpy change of atomization. Now, how to calculate these enthalpy changes? What we can use a Hess law, or application of Hess law is a Born-Haber cycle. What is the Hess law? It states that overall energy change is independent of the route or the path which we follow. So energy change does not depend on what route or what path we are following. Example, say you have A and B are the reactants. they're forming a product C. But the second possibility, first A convert into E or D, and that D reacted with B and formed C again. So if the same product is formed by different routes, the overall energy change is independent of route. Like example, if here the energy was 30 kilojoule per mole, this side the energy was example 20 kilojoule per mole, and here the energy will be 10 kilojoule per mole. So you can see the overall energy change if I follow path 1 or if I follow path 2, the overall energy change is independent of the route. That's why we call that, according to Hess law, so we can follow any route and work out the energy change or the enthalpy change using this concept. So example, say a reaction is there between hydrogen and chlorine to form hydrogen chloride. So you have a reaction, hydrogen hydrogen gas is reacting with chlorine gas, and it will form hydrogen chloride, HCl. So how you can make a route here, how you can work out the route. So if hydrogen gas react with chlorine gas, it is forming hydrogen chloride gas. That is one possibility. What is the other possibility? Maybe we have hydrogen atoms and then we have chlorine atoms in a gaseous state, and they will form hydrogen chloride. And how we draw an arrow, because we can convert the element into atom. So now the two routes are there. This is route 1, that hydrogen and chlorine, the element, react and form a compound. Or second thing, first they convert into atom and their atom directly form the compound. So this is a route 2. So according to Hess law, the overall energy change is independent of the route. It does not depend on the route or the path which we follow. Like example, if I am saying the energy for this reaction is delta H1, example, energy for this change, the overall energy change delta H2, and for this one delta H3. So how to work out where is the start of the cycle and where is the end of the cycle. So where the two arrows are pointing out, so the position where the two arrows are pointing out, that is the beginning or the start of the cycle. And where the two arrows are pointing in, that is the end of the cycle. So if I follow according to this Hess law, if I follow route 1 or I follow route 2, I will get the same energy change. So according to route 1, if I start from H2 and Cl2 and form HCl, the route 1 means the energy change is delta H1. And that will be equal to the root 2 delta H2 plus delta H3. So delta H1 is equals to delta H2 plus delta H3. So same way, if we know delta H1, we know delta H2, so we can find delta H3. So unknowns we can rectify or identify here. So example, so you have H2Cl2 and it is forming HCl. So what is the one possibility that this is in terms of energy, because what happened to break the bond we have to supply energy. Bond breaking or atomization is always endothermic. So here the reactants are there and you have the product. So what happened? First, you have hydrogen and chlorine. You supply energy to hydrogen and chlorine, so they atomize. This is one thing. If the arrows are pointing up, it means that is exothermic reaction. If arrows are if arrows are pointing up, that means it's an endothermic. If it's pointing down, then it will be exothermic. So to understand this cycle, like hydrogen and chlorine, they absorb energy, they form hydrogen atom and chlorine atoms. Then hydrogen and chlorine can react to form hydrogen chloride. Or hydrogen and chlorine, we can break the bond and form hydrogen atom and chlorine atoms. Now, how to identify what are the routes? So always where the two arrows are pointing out, as you can see in this part, the two arrows are pointing out, that is the start of the cycle. And where the two arrows are pointing in, that is the end of the cycle. So what is the route 1? So according to this is route 1, only one arrow. And what is route 2? This is route 2. So if I follow any route to get the same answer, so route 1 and route 2, so according to route 1, the energy change is A. According to route 2, the energy change is delta H and plus B. But if I need delta H, so it will be A minus B. Is it clear, this example? Is it clear? No, arrow of the B is not other way around. It is actually showing like which direction you are taking. It's not about the signs, because basically what happened, reactant form a product of, it's like if we break the bonds of hydrogen and chlorine, we'll get hydrogen and chlorine atoms. If we break the bonds in hydrogen chloride, we will also get hydrogen and chlorine atoms. That is why the arrow for B, it is shown upward. If we are, this is what we are taking. Any doubt in this till now? We'll do the numericals as well, but the first thing is how to apply the Hess law on these chemical reactions which are having a multiple routes. Same way, another example, look, this is, say, this is a simple example for energy change is given. Now, first thing is you have to identify the start of the cycle and end of the cycle. So where the arrows are pointing out, that is the start of the cycle. So means this is the start of the cycle. And where the arrows are pointing in, that is the end of the cycle. So overall energy change is independent of the route. It does not depend on the route or the path. So we can say if we follow root 1 or we follow root 2, we'll get the same energy. So we can say A plus delta H is equals to C plus D. So if, for example, delta H is unknown, A will go other side, so C plus D minus A will give us value of delta H. So another example related to Hess law. Example, we have anhydrous copper sulfate. Anhydrous copper sulfate absorb water molecule and become hydrated copper sulfate. The energy for dissolving of hydrated copper sulfate and anhydrous copper sulfate is given. So if you have copper sulfate solid, we add water or dissolve, make an aqueous. The energy is given minus 600 minus 66.1 kilojoule per mole. And if we have hydrated copper sulfate, the energy is given 11 kilojoule per mole. Now, if we apply the Hess law here, where the two arrows are pointing out, then how to make a cycle is another thing. But first thing is how to apply this law. So where the two arrows are pointing out, that is the start of the cycle. And where the two arrows are pointing in, that is end of the cycle. So what is the root 1? According to root 1, this is root 1. And what will be root 2? This is root 1 and this is root 2. So according to root 2, I can say delta H plus 11 kilojoule per mole is equals to minus 66.1. If we need delta H, so what we can say, delta H is equals to minus 66.1 and minus 11. So delta H is equals to minus 77.1 kilojoule per mole. Is it clear? This example applying a Hess law. Now example, sometime you have reaction with like you have the same product. Like example, when calcium carbonate is reacting with hydrochloric acid, it gives calcium chloride plus carbon dioxide plus water. And so using this, what we can find the hydration energy. So if you want to find the hydration energy, what will be the parts we should include? Anhydrous salt, this is solid, anhydrous, hydrated, both are solid. When we dissolve, this is aqueous one. So the points for finding the hydrated enthalpy change of hydration, the anhydrous salt will be there, hydrated salt will be there, and aqueous. Same thing, if we want to find the enthalpy change of decomposition or energy required for decomposition, so what we can do, like calcium carbonate can decompose into calcium oxide plus carbon dioxide. Now what happens if this calcium carbonate react with hydrochloric acid, it gives calcium chloride, water and carbon dioxide. Or if this calcium oxide react with hydrochloric acid, it gives calcium chloride and water, but because the carbon dioxide was already there, so it will remain as it is. Now again, if we apply the Hess law on this, where the two arrows are pointing out, that is the start of the cycle, beginning or the start of the cycle. And where the two arrows are pointing in, that is end of the cycle. So what is the route 1 and what one is route 2? So calcium carbonate can react with hydrochloric acid, give calcium chloride, water and carbon dioxide. So what we call this, we call that as example delta H1. Because right now we are discussing how to use the Hess law to make the expression. And say calcium oxide react with hydrochloric acid, that's it, delta H2. And therefore decomposition of calcium carbonate into calcium oxide and carbon dioxide is delta H. So delta H is equals to delta H, like this is root 1 and this one is root 2. So we can say delta H plus delta H2 is equals to delta H1. If delta H2 move other side, it will be delta H1 minus delta H2. The reason is that because for and why this Hess law or a Born-Haber Hess law is important for us, because for thermal decomposition reactions practically it is difficult to find the enthalpy change. Why? Because you have to supply energy and you have to calculate how much energy is being absorbed, so which is a difficult thing to do. That is why we use a Born-Haber or we use a Hess law or application of Born-Haber cycle to work out the enthalpy change. So this cannot be done experimentally because it is impossible to add a heat required to decompose a solid and measuring a temperature of a solid at the same time. Like if we are supplying heat energy, maybe we supply 100 joules, 200 joules, but we don't know whether this is 200 joule is sufficient or whether it is small to break amount of energy to break down the solid. So practically we cannot find for endothermic reactions, we cannot find the enthalpy changes directly. For that we use a Hess law. For exothermic reactions we use a calorimeter to work out the energy released, because they release energy, so we can work out how much energy will be released. Now using the Hess law to determine the enthalpy changes of formation. So right now till now what we discuss, first thing what we discuss is if we are finding the enthalpy change of hydration. Enthalpy change of hydration means energy released when a water molecule are added to the compound. So what we can do, we can have anhydrous salt, hydrated salt, we add water, so it will become aqueous. Or we can also use the thermal decomposition, the enthalpy change of decomposition of the reactant. So for that purpose, what you should have the substance which can react with both the reactant and product and give the same product, as in this example, like hydrochloric acid or any other acid which react with carbonate or metal oxide, give the same result. Is it clear till now? The concept of enthalpy change. So we started with chemical energetic, we started with endothermic, exothermic reaction, energy diagram, then standard enthalpy change of formation, combustion, neutralization, atomization, and we are discussing the Hess law.